Hello everyone, I'm Alex. I'm going to be presenting today about some work that I did during my bachelor's with Dr. Tatiana Barron at the University of Western Ontario, although now I'm starting my master's degree at Waterloo under Dr. Graham Smith, so hence the dual affiliation. It's going to be talking about coherent states, how you can sort of measure their entanglement and some geometric aspects of that. I've tried to make the math very simple and very light, so it's easier for everyone involved, including me, and so let's begin. So where are we going to live? We're going to start out with some sort of classical theory, which for us will amount to some sort of manifold that will have some sort of structure. And with that manifold, as was nicely explained in the previous talk, we can sort of quantize it, and you end up getting some sort of a Hilbert space where you can end up having a quantum theory there. Now, this Hilbert space that you have takes in a couple of things that will have some sort of quantum states that live there. Really, these are vectors, but you can associate them with pure states, but those are just words. And some sort of quantum parameter, typically, that has some sort of physical interpretation behind it. Now, what's our idea? Well, there's these nice types of states called coherent states that allow us to sort of trace out the geometry of our original manifold inside that Hilbert space, because we can make an association with points on the manifold and send them into vectors over there, and then take the pure states. So if we can somehow entangle two of those coherent states, then we can think of measuring their entanglement, the entanglement entropy, as a function of where those points lie on the manifold. And so you can ask questions like, oh, what happens is you move the points around, what happens is you change that parameter, the quantum one there, right? How does this entanglement change? That's the sort of question that we want to answer. So this is not a talk on geometric quantization, but a high-level overview of what actually amounts to producing this Hilbert space is you start out with your sort of classical space, the symplectic manifold. It has some structure with it. It has a Poisson bracket. You have some sort of Hamiltonians that are just smooth functions in the manifold that capture dynamics. And the goal of geometric quantization, broadly speaking, is to find some sort of nice representation of your space of smooth functions in the sense of representation theory. And you want it to sort of preserve some structure. So there, you want some Hilbert space, and you want to have this nice mapping that preserves these brackets. But the important thing for us is that you can produce a Hilbert space. The exact details about how you recover it aren't terribly important for us. We just need the end result. So if you add some extra structure onto your manifold, if you assume that it's Kähler, then there's a particular quantization scheme, Weierstrass quantization, that'll produce these quantum Hilbert spaces, and the parameter there, which I alluded to at the beginning, are just going to be non-negative integers, right? So for each one you can produce it, and so that's where we can sort of take a look at limiting effects, especially because these are supposed to have some sort of physical meaning there. It's supposed to be sort of the reciprocal of the Planck constant, so as you push k towards infinity, it's supposed to have some sort of semi-classical limit that you recover there, which is why we're going to be taking a look at sort of asymptotic results. The one space that we'll focus on is a relatively simple one because it's the easiest to build up the theory for. It's going to be when your manifold is just Cn, and then it turns out that the quantum Hilbert spaces there that you end up producing are going to be the Segal-Barton spaces. So these are just spaces of holomorphic functions that are integrable with respect to some fancy little weight. So it's d mu, which is just the Lebesgue measure dz, but with this sort of Gaussian factor added on top. So that's the structure of the Hilbert space that we're going to be looking at there. So what are these coherent states? Well, if you're very lucky, like we are for that Segal-Barton space, and then these quantum spaces that you produce are reproducing kernel Hilbert spaces of functions on your original manifold, then just through the Riesz-Fréchet representation theory, you can end up recovering for each point in your manifold some sort of vector that lives inside the Hilbert space, which are these capital thetas. And they have that reproducing property, but the important thing is they are the ones that give us this mapping, right? And there's a very simple description in the case of the Segal-Barton space of what these reproducing vectors, functions, coherent states actually look like. You can write it down very simply. So that's what we're going to entangle, but how do we actually entangle that? How do you measure it? It's a little bit of a sensitive topic when you have an infinite dimensional space like this, because you have to worry about, does your notion of entanglement, the thing that you're measuring, actually make sense? So there's a little bit of notation, but if you have some sort of separable Hilbert space, and you let V be its tensor product, which is where, with itself, which is where the entangled states are going to live, we're going to say that T, an endomorphism on H, is trace class if this definition of trace makes sense, right? So this has to be well defined. It has to, not matter what sort of orthonormal basis that you pick. If you reorder it, sometimes it does, and then trace doesn't make sense there. But for the ones that do, we'll call those trace class. And we're going to need a separate notion, which is going to take us from this tensor product down into a single component system, right? And then that's given by partial trace, which is if you have an endomorphism on the tensor product, then it's going to be an endomorphism back down on one of the original component Hilbert spaces. And that's just an operator that's defined by satisfying this inner product relationship for any x and y in H. So this will make sense if S is trace class in V. So the specific type of entanglement that we're going to look at is entanglement entropy. So to us, a quantum state, it's going to be an endomorphism on V, which is H tensor H. It's going to be positive, self-adjointed. It has to be trace class, and its trace should be equal to 1. That's what we desire. And the specific types of states that we're going to be looking at are pure states, right? So if rho is rank 1, if it's just a projection onto some sort of vector, then we call it a pure state. And that's how we can make the association between having a vector in your Hilbert space and then having a pure state, because you just look at the projection onto the ray described by that vector. Now, entanglement entropy is this fancy looking calculation there. You take your projection onto a vector V, then you take the partial trace, then you compute this x log x function, but you extend it to operators, and then after that you take the negative trace. What does that really mean? It's basically something like spectral entropy. You take the Shannon entropy of the eigenvalues of your reduced state. Why do you care about this? Well, one way to interpret entanglement entropy is that it's going to always be a non-negative quantity, but it's going to vanish if and only if the vector that you're projecting onto is decomposable. So if you can find some x and y in H so that V is equal to x tensor y. And the more positive that this entanglement entropy is, the more non-decomposable you are. So in some sense, the more difficult it is to write it like that. We can extend notions of entanglement entropy to mixed states, which are states that are just sort of convex combinations of pure states. But that turns out to be a lot more difficult to work with, and it's not clear if there's sort of the best way to extend it. But those methods do exist, your convex roof constructions, but we won't be discussing them. They're just there for fun. So the specific type of states that we're going to be looking at are what we call Bell-type states. So if you just take points U and V, that live in this Hilbert space that are non-collinear, so they're not going to lie on the same ray, then we're just going to take U tensor U plus V tensor V, and then you just normalize everything, right? So that you end up with nice unit vectors. These are just sort of moral analogs of the Bell states that are used in sort of quantum information computation. They don't necessarily have the same behavior, right? In particular, if U and V aren't orthogonal, then they can behave a little bit differently, but they're just pretty nice to write down. And we'll see that these are actually always entangled because of this non-collinearity condition, right? The other important thing for us is that now we have some manifold somewhere, right? That's where we began. So we can take a point, 2 points there, P and Q, and we can naturally talk about the Bell-type state associated with those 2 points, because you take those 2 points, you map them to 2 coherent states, and then you take the Bell-type state associated with those there. So you can sort of pass it all the way through, and this final quantity there, B sub k PQ, is what we're going to be looking at. So we have this general lower bound here for just any of those Bell-type states. The proof for this isn't terribly interesting. You just compute it, and then you just use an inequality there to make it look a little bit simpler. What's nice, though, is that it's given in terms of sort of norms and inner products of the vectors that you have there. And again, if U and V are not collinear, then this is always going to be a positive quantity, the lower bound will be, so we know that we'll always have an entangled state, right? Which is interesting because we want entanglement for sort of physical reasons. And then this is the main result there that we have for Cn, so for the Segal-Bargman space. So again, if we do that, if we take 2 points there, PQ, send it to coherent states, take the bell-type states. Then we have this lower bound for their entanglement entropy, right? And it's given as a function of the distance between points P and Q. And that's sort of where the geometric aspect comes in. So as you sort of push these points further away, you have more and more entanglement. People care about this because entanglement is useful as like a physical resource. It allows you, it quantifies how much information you can transmit. So if you have some entanglement, this is generally a useful thing for you to be able to do. So it's nice to be able to quantify, maybe because you can't exactly compute it, but at least how much do you have, right? In this very nice sort of simple formula through this process. It also has a little bit of that geometric connection with that. The way that you get this result is you just take that general lower bound, that sort of lemma, and then you just have to apply some sort of asymptotics on those norms and inner products, which is why we have this asymptotic result. So you'll be able to find some k, henceforth this lower bound will hold there. And for these coherent states in the Segal-Bargman space, again, we'll always have this entanglement there. So this is nice. Maybe isn't the nicest thing to picture geometrically. There's a little bit of a prettier example, but to set it up, it's a lot of words, so we'll just kind of go over it at a very high level. So if we have M in this case being CP1, which for us we'll think of it as a sphere, then we'll sort of take by faith that you can associate a Hilbert space with it, which is just going to be these complex polynomials of degree 1, which will have this magically arising inner product there. Right? Doesn't matter how we got there, but the point is that it exists. Now, we're going to take the sphere, we're kind of going to poke a hole at the top, and we're going to stereographically project it onto the plane, just for it's easier to think of it that way. And then we're going to take our points P and Q are just going to be some point x and then some point negative x that lies on the real line inside the complex plane. And so now we've sort of reduced this entanglement quantification thing to a single variable, it's x. So how far away are these points from each other on the real line? I mean, this is just a number. You can work it out. It's very tractable in this case because the space is so simple. And so you can exactly compute what it looks like. And you have this graph here.
Space, H is what?
It's the span of complex polynomials of degree 1. So 1 in Z is your orthonormal basis.
It's a finite dimension.
Yes, dimension 2. And this is the exact expression for what the entanglement entropy of these bell-type states will end up being there. And it has some sort of maximum there, right? And that maximum is when x is equal to 1, where does the geometry come in? Well, if you pack the plane back up, if you undo that projection, this will be maximized when they're diametrically opposed to each other, right? So if you take 2 points on the sphere, this entanglement is maximized once they're on opposite sides. Sort of this should make sense because our previous lower bound was, again, a function of the distance, an increasing function of the distance between them. The same thing here holds for the sphere, even though it's for a different space. Now you can sort of generalize this result to other compact manifolds, but that's a lot of words, and I'm not going to read all of this, but the idea is that you have a similar result there. It's a very similar looking bound. It just has some more constants there because you have a more general space that you like to work with. And that's all I have, and thank you very much for listening.
Thank you very much for this nice talk. Mm-hmm. Are there questions or comments? Okay, so maybe I have a question. Mm-hmm. So here you have this theorem, mm-hmm. And what about what about M non-compact, like for example?
We tried to look at that. I don't believe it was very tractable to end up having a result sort of this clean. The non-compact case that we looked at specifically was CN.
Yeah, sure.
There, the Segal, it's the easiest to work with.
Curved non-compact.
Yeah.
Like hyperbolic plane, for example.
Sorry?
Like Siegel plane or Siegel space or hyperbolic plane or whatever Hermitian symmetric space or.
I don't think that we tried to look into those. We mostly we try to work it out for this compact case, and then after that, the Segal-Bargman space is sort of a toy example of a non-compact one.
Because there you have reproducing kernel Hilbert spaces.
Yes. So yeah, you should be able to recover some similar results to that there. But yeah.
Okay. Mm-hmm. Okay. Thank you very much. Okay, so there is no fourth speaker. He should be here as my student, but he couldn't come. session is over. Thank you.